All right. So you should all be seeing my notebook page. In a moment, I'm going to be starting section 1.1. But before I do that, I just want to show you how you can calculate your grade. So if you want to do this because you know what your grades are, right? So you have an exam grade. I'll just say, and by the way, the average on the exam was an 85. So let's say you have an 85 on the exam, and you have your two quiz grades. We have, let's say you got, I'll go a little lower here. Say you got a 70 and an 80 on the quizzes, okay? And we know our exam grade is 35%, and our, I'm sorry, I have it backwards. The exam one is worth 15%, and then the quiz grades are worth 35%. All right, so here's what we'll do. For the exam grade, you're going to take 85 and multiply by the decimal version of that percent. So I should have made it a little easier for me to do that because I'll need my actual calculator. So let's see what 85 times 0.15 is. I'm going to keep a lot of decimals here. So that's 12.75. And then let's see the average of our quizzes, right? So it would be 70 plus 80 divided by 2, right? So that's going to be a 75. So we have a 75 quiz average, and you multiply that by the decimal of 35. That comes out to be 26.25, all right? Now, you're going to add up these two numbers, so 12.75 plus 26.25, and you get a 39, all right? Now, that's not a 39% out of 100. That's 39 divided by how much percent that we started with, which was 50%. So it's really, this is 39 divided by 50. So then our decimal final average as of right now with these fake grades is a 78%. Okay? So that's how you could figure out where you stand in the class. You can go through this exact same process. So what I'll do is I'll leave this here, and this is in the section 1.1 notes, so you could see exactly how to go about figuring out where you stand. Okay? All right, so with that being said, I'm going to now start section 1.1. So as I go through and once I do an example, I will try my best after every example to ask if there's any questions and then wait to see if there's a hand raise. But, if I'm, going through these notes and, I forget to do that, feel free to unmute yourself and just tell me to hold up for a second. Oh, we got a hand raised. There we go. Perfect.
I don't know if you had said it already. Are you still going to put up the notes that you have written out for today on D2L?
Yes, so on D2L, I'll actually show you that. Let's see if I could just stop sharing this and reshare. Sorry, there's a 1,000 screens open. Not 1,000, that was a little exaggeration. When you go on the D2L site, if you go to class notes link, this link is actually a live version of whatever I have in this notebook. So when I click that, it actually takes me to the exact note page. Hold on, let it load. So actually, if you go to section 1.1, hopefully all that stuff I just did is there. Yep, there you go. Yep, so when you click that link on D2L, it's taking you literally to the exact same notebook. So everything will be there. Okay, Tommy? All right. Any other questions? All right. So let's go back to the notebook and start section 1.1. All right, so section 1.1 is on linear equations of one variable. All right. So some of this, again, hopefully is a review for a lot of you, because I know at some point you've seen, a lot of this stuff. So if I just can briefly define what we mean by equation. So it's just a statement with two expressions that are equal. All right? Because we use the equal sign to separate the expressions. Okay? So if we had something like 5x minus 4 equals 3, what we're saying is the expression on the left must be equal to the expression on the right. Now, you're going to see as we go through some examples today that you can go ahead and make these, but it doesn't necessarily mean that they're going to be an equation that has a solution. And there's a couple different types of linear equation types that I'll show you today. All right. So this particular, when we define linear, we just mean that's an equation with one variable. And generally the variable we use is x, but really it could be absolutely any variable that you want to use. Okay, so one property of a linear equation is the domain, and we've been talking about the domain a little bit with our rational expressions, but I want to give you a little better definition. So the domain is the set of real numbers that allows both sides of the equation to be defined. All right, so it's a set of real numbers that allows both sides of the equation to be defined. So if you remember with rational expressions, we looked at the denominator a lot because if the denominator was 0, the expression was undefined. So there could have been real numbers that are not in the domain of those expressions. But now we're going to be dealing with an equation. So instead of just one expression, we have to look at both expressions. So both expression 1 and expression 2 have to be defined when we plug in values of x. Okay. Okay, so let's look at this example that I had wrote up here because I'm going to kind of go through some of the process or some of the things the end of chapter problems are going to ask you. So we have this 5x minus 4 equals 3 linear equation. All right. So we want to figure out its domain. Okay. Now, there's only a couple of things that you're going to have to look for in this section when dealing with the domain. You'll have to look for rational expressions, so that's going to be fractions with variables in the denominator, or you have to look for square roots. So for this particular equation, we do not have rational expressions, and we don't have a square root. So in that case, the domain we simply say is all real numbers. Okay. Now, we're going to introduce you, this book introduces something called interval notation when defining the domain of an equation. So if your domain is all real numbers, here's what the interval notation version of the domain would look like. And you've probably seen this before. Okay, so this is basically saying from negative infinity all the way up to positive infinity, all of those real numbers satisfy this equation, or essentially mean that it's defining both sides. Now, anytime you use, or you have to use an infinity symbol in an interval notation, you have to use parentheses. But there's two types of sort of bookcases you can have on these intervals. You could have a parenthesis, or you could have a bracket. So the bracket includes the value next to it, and a parenthesis does not include. So just with infinities, since we really can't define infinity as an actual number, we use the parentheses. Okay? And then some other symbols that we might see with the domain would be, this kind of looks like a U, but it doesn't have any like tail at the end of it. It's just sort of a curvy U like this. This is the union. Okay? And then this guy is the intersection. You're going to see this throughout the rest of the course. Okay? But for the domain for all real numbers, that one's easy because you just have to remember that it's negative infinity to positive infinity. Okay? All right, so what you could do with this equation is you could solve it for x. Right? So 5x minus 4 equals 3. At this point, you know, you've definitely learned how to solve a linear equation before, so the book doesn't really spend too much time on it. So you would add 4 to both sides, so it gets rid of the 4 on the left, and then adding 4 to the right side gives you 7. I mean, if you've learned to, you know, do something like this, you know, that's absolutely fine. Whatever process you've learned to do is cool with me. And then to isolate the x, you know, we're going to divide both sides by 5, and you're going to get 7/5. All right, so when we solve a linear equation for x, we call that, this is the solution to the equation. Okay? But you might be wondering, well, you just said the domain is all real numbers, meaning we can plug in any number for x and both sides are defined. Well, having both sides defined and then having a solution to the equation are two different things, and I think a lot of people sometimes get those things confused. So let's say, as an example, let's say I plugged in, let's say x equals 1, right? So that's a real number, and that's a part of our domain, right? That's in the set negative infinity to positive infinity. So let's just plug that 1 in and see what happens. Now, anytime we're not sure if the equation is going to be true, sometimes you put this a question mark above the equal sign because you're not entirely sure if it's going to work. And then you'd have 5 minus 4, question mark, equal sign, 3. So this 1, 3. So we know 1 does not equal 3, so you're going to see a lot of dashes through equal signs. All right, so 1 does not equal 3, so that just means this is not a solution. Okay? So you could have values of x that are not solutions to the equation, but they are in the domain. All right, and because we're talking about a linear equation, linear equations can only have, one solution. All right, so that was a lot of information, and it's stuff that you've probably heard at some point, but are there any questions? Please feel free to ask at this point. We're okay? All right. Okay, so let me give you another example. So the first couple types of problems here will be, they're going to give you an equation. So I'm going to give you one with a rational expression. So say we have 4 over 3 minus x equals 5. All right, so we have an equation, 2 expressions. All right, so again, let's find the domain. Okay. So the domain here, again, we don't have to worry about the 5, right? There's no variable over there, so don't have to worry about that. We're just looking at the rational expression. So just from the work that we've done in the P sections, we could see just by looking at this that when x is equal to 3, you get a 0 in the denominator. So the domain, if you wanted to write it out in words, would be all reals except x equals 3. All right, now we want to write that in interval notation. All right, so I'm going to give you all the different types of interval notation that you're going to have to know for this section. So when you're doing the homework and it asks for interval notation, just go back to these examples and you'll see how this works. All right, so for interval notation, again, all reals, which means we're going to start at negative infinity and we're going to go all the way up to 3, all right? And since we do not want to have x equals 3, I'm not going to use a square bracket. I'm going to use a parenthesis, which means I'm going from negative infinity up till 3, but not including 3. All right, but I'm not done yet. Now what I want to do is I want a union, which essentially just means you're adding those two intervals together. And then again, I'm going to start at 3 because I'm not going to include, so I use a parenthesis, and then it'll go all the way up to positive infinity. Okay, pretty good? Awesome. All right, so now how do you solve this equation? And this is actually a question I'll ask. Who wants to answer it? Raise your hand and ask. How do you solve this equation? What do you think the first step would be? Anybody?
Cross multiply.
Absolutely. Who said that, by the way?
Lauren.
Oh, hi. Hi, Lauren. So we're going to cross multiply. So really this 5 over here is 5 over 1. So we'll cross multiply and we'll get 4 times 1, so 4, and then 5 times 3 minus x. So now it becomes a pretty simple problem. I'm going to distribute that 5. So we're going to have 15 minus 5x. And then I'm going to subtract 15 from both sides. We're going to get negative 11 equals negative 5x. And then I'm going to divide by negative 5 so the negatives cancel, and I get 11/5. So 11/5 is our solution. Okay? Hopefully that makes sense. All right? Now, there are going to be some times when you have rational expressions that look like this. So here's another example. Let's say you had 2 over x squared plus 4x minus 5 equals 5. Okay. What are we going to do here? Because we're interested in finding the domain. So to do that, again, we're trying to figure out what values of x in this denominator make it undefined. So the first thing we're going to have to do is factor it. So hopefully at this point we're pretty good at factoring. We spent a lot of time on it. So we factor the rational expression, so we know this has to be x and x. This has to be 5 and 1, and then this should be positive, this should be negative. All right, and that's still equal 5. Okay, so now we know the two possible terms to make the denominator equal, right? If x is negative 5, right, clearly we're going to have a 0 in the denominator. Or if x is 1, right? So the domain here is going to be all reals except x equals negative 5 and x equals 1. So what does that look like in interval notation? All right, so negative 5 is the smaller of the two numbers. So again, we start at negative infinity. We're going to go up to negative 5. We do not include it, so we use a parentheses. Now we union that with negative 5 is going to go all the way up to positive 1, not including those two, and then union that with 1 all the way up to positive infinity. So these set notations are very specific, but again, it's a little bit more mathematically correct than just using words, okay? So that's why, and then we're going to use these interval notations a lot in some later sections, so they're sort of just introducing it to you now to make sure that later on, this won't be the first time you've seen it. Okay, any questions on that one? All right, seeing none, we'll move on to the next example. Now this will be the last type that we'll see in terms of how to figure out domains. Let's say you had the square root of x minus 5 equals 30. All right, and we want to figure out the domain. Now, this problem, we're not necessarily looking for something that's undefined, but we are concerned with whether or not any value of x could make the either expression to have an imaginary number, right? So a real number and imaginary number are not the same thing, and for the domain, we can't have imaginary numbers. So how can we check to see if this is going to hit, what x values make this imaginary? Well, you take the thing inside the radical, right? We actually call that the radicand, if you remember. So you take that And in order for that square root to produce a real number, the radicand has to be greater than equal to 0. Right? Because if that square root has a negative sign underneath there, we would say that there's an imaginary solution, and we can't have that in the domain. So what you do is you solve this. This is an inequality, okay? But they kind of work just like equations. So again, if you wanted to isolate the x variable, which is what we want to do, you'd add 5 to both sides and get x is greater than equal to 5. So the domain in words would be all reals where x is greater than equal to 5. And just as a reminder, if you plugged 5 in, you'd get the square root of 0, which is 0, which is a real number. So you are including 5. So the interval notation, all right, is going to look like this. It has to be x is greater than equal to 5, so we're going to use a square bracket because we want to include 5 this time. And x just has to be greater than that, which means we go all the way up to positive infinity. But again, we use a parenthesis. That's a terrible parenthesis. I want to make sure you know it's curved when you look back at it. And we know that we can't include positive infinity. So that would be the interval notation for the domain. All right, any questions on that? So that process will be the same for all square roots. You take the radicand, set it equal to greater equal than 0, and then isolate x, and it basically gives you your domain. Okay? All right, wonderful. All right, so that's one type of problem, and they're pretty simple, I think. All right, here's the next thing. Again, solving equations. And they give you these big god-awful ones. It's not that they're difficult, but it really wants you to understand and get used to using order of operations. So you've probably seen this thing before. And I don't know if I mentioned in class that I hate acronyms for things. Like, I hate it. But you've all seen this before, PEMDAS, right? So P is parentheses, E is exponent, M and D are multiply and division. And really, these can go either order. And then A and S are addition and subtraction. And again, they can go in either order. Okay, so they give you an equation that looks like this thing. Here's an example. All right. So just by inspection, there's no rational expressions and there's no square roots. So the domain of this would be all reals. So I'll save the time and not even write it down. But it wants you to go ahead and basically do order of operations to solve for x. All right, so you're going to do parentheses first. So you would do parentheses inside parentheses. So and I'm going to painstakingly go through each of these processes first. Again, if you're really good at solving these, you can take whatever steps you'd like, but I'm going to go through each of these. So I'm going to do the parentheses that are inside these square brackets, which are also parentheses, and do negative 2x plus 4. All right, and then I'm going to do all this stuff in the square brackets. So I get 3x minus 2x, which is x, so x plus 4. And I'll just put those in regular parentheses. You can change square brackets to parentheses at any moment. That's fine when you're solving these equations. So x plus 4. All right, now the reason I did that here was because this negative sign is going to be distributed in this binomial, x plus 4. So x, it'll be negative x minus 4 equals 11. Then we'll have, again, now we only have subtraction, but you could do them in any order, but I'll do the x's. So we have 5x minus 4 equals 11. Now I'm going to move that 4 onto the other side. So I'll add 4 to both sides and get 15, and then finally divide by 5 and get 3. All right. All right, so we get 3. Now, that would be the solution, so long as we just did everything correctly. So the book's going to ask you, and at least for at the beginning, you should check to see if this is actually true. All right, just like if you would check, like when you had a polynomial and you wanted to factor it. You know, when you get your two binomials and you're multiplying them together, and then you FOIL them out to see if you get the same answer. Sort of the same thing here. What we want to do then is then plug 3 back into this original equation. So 6 times 3 minus 3 times 3 minus 2 times 3 minus 2 equals 11. All right, so we'll skip a few steps here. So we're going to do 6 times 3, so we have 18. So inside the parentheses here, we have 3 times 3 is 9. Now this 3 minus 2 is a 1, so it's minus 2 times 1, so minus 2. So then it's 18 minus 9 minus 2 is 7. And then you get 18 minus 7, which is 11, equals 11. Boom, there it is. So we just checked to make sure that x minus 3 is indeed a solution. Okay, wonderful. So that's nice when you have an equation and you actually get a number that turns out to be a solution. Now there could be, first off, any questions on that? Is that all right? Just solving equations? All right, I'm pretty sure we're probably okay on that. But you might run across equations that look like the one I'm about to show you. All right, so one very similar to the one we just did. Right? I mean, same sort of structure. So we know what we have to do. So let's go ahead and solve it. So we get 5x minus 3x plus 2x minus 2. So 5x plus 2, or 5x minus 2 plus 1. So look what happens. You got 5x minus 5x, so that goes away, and then it's distributing a negative 1 and negative 2. So you end up getting 2 equals 1. Well, we know that's not true. Okay? So when no x value solves this equation, and you know that's going to be true when this happens, when you get two numbers, two integers or two decimals, whatever, on either side of the equal sign, and they're not the same, we call this type of linear equation, we call it inconsistent. Okay? Inconsistent when this happens. All right, so that's one thing you could run into is a linear equation that's inconsistent. Here's another type, and I'll just put these next to each other because there's not that many problems that you have to worry about here. Usually if we have an equation, it's actually solvable. So lots of stuff going on here. So I'm going to do the parentheses first. Okay, we're all good with that. So what do we have here? 1 and the 14 is 15, and the negative 5y plus 2y is negative 3y. And then over here we have 15 minus 3y. And if I subtract the add 3y to both sides, I get 15 equals 15. Okay, so what does that mean? When you cancel out all the variables and you're left with integers that are exactly the same. This is an equation, is an identity. And what does it mean to be an identity? It means any y value satisfies the equation. So the domain of this one, right? I'll write this one out. The domain, we don't have any rational expressions or square roots. The domain is all reals. So that means the solution to this equation is basically the domain. So when you have an identity, any number that exists in the domain satisfies the equation. So if this happens, it's an identity because it doesn't matter what y value you plug in from the domain, you always get the same thing. All right, questions? Okay, good. Wonderful. All right. We're going to go over one more type of equation to solve. And this is going to be equations with multiple rational expressions. All right, these will be the ones that are the trickiest ones. So let me just throw one out here so you know exactly what I'm talking about. Say you had right, so clearly we have multiple rational expressions. Okay. One thing you could do is you could combine the rational expressions that have the denominators that are the same, like you have the 2 7s there. But there's one process that will work every single time. All right. When you look at the denominators, right, you see that the 7 is repeated. All right, so you're only going to do 7 one time up here, and then you multiply that by whatever the other denominator is. So you have 7 times 3, so you get 21. All right. So what you're going to do is eliminate the fractions from this linear equation by multiplying the entire thing by 21. All right, so here's what that's going to look like. So I'll just leave 21 there for the moment. All right. All right, now what we do is we want to try to reduce these rational expressions to lowest terms. So what happens when you multiply by this 21 value, you're going to see in this first rational expression here, the 7 cancels out, you're left with the 1. This number becomes a 3. In the second rational expression, the 3 crosses out to be a 1, the 21 becomes a 7. Right? I'm just reducing these fractions, and that's 1 and that's 3. So now if I rewrite this, it now becomes a solvable linear equation. So our first goal in these rational expression equations is to eliminate the fractions, eliminate the rational expressions. So now I can just go about my business here. We'll get 6 minus 9x plus 7x minus 1 equals 9x. So I'm going to keep all the x's on the right-hand side. All right, so that means I'm going to add 9x, right, to get rid of this one. Subtract 7x. So that's plus 9x minus 7x. So what we're going to have on the right-hand side is 18 minus 7, so 11x. And then the integers left on the left side, it's just 6 minus 7, so negative 1. So then x is negative 1 over 11. So that is the solution to this equation. And by the way, the domain here is also all reals, because we don't have any x terms in the denominator, so we don't really have to worry about anything being undefined. How we doing? I'm going to do another one of these, but any questions up to this point on that process? So far, so good? All right, great. All right, here's another one. Again, there's a bunch of fractions. Some no fractions. Okay, so there we have it. Now, really, this 2x, it's really 2x over 1. So when we're trying to figure out what to multiply, you can sort of just ignore that 1 if you'd like. All right, so what was the process? So you take all the numbers and you ignore ones that are repeated. You only do the one. So we have a 3 in the denominator, the first one, and then a 2, and then a 6. So 3 times 2 is 6, 6 times 6 is 36. So I'm going to multiply everything in this equation by 36. So 36, I'll put it up here so I'm not rewriting the whole thing again. 36 times this whole thing. So 36, sorry, it's going to take a couple seconds to write all that out. All right, now you just go about simplifying these expressions. So the 3 goes into 36, I believe, 12 times. We'll leave this one alone for a second, and then 6 goes into 36 6 times. So we'll have 12 times x plus 4, plus this 36 times 2x is 72x. 36 times a half is 18, and then 6 times 3x plus 2. And then now it just becomes a linear equation with no fractions. So let's solve it. So I'm just distributing all the integers outside these parentheses. Okay, what are we going to do here? I guess what we'll do is we'll subtract 18 from this side, 18x, and then we'll have to subtract 18x over here. All right, so what do we have here? We have 12x and 72x is, actually this will be easier. 12x minus 18x is negative 6x. So then negative 6 and 72 is 66x. And then what we're going to do is 48 minus, so we'll subtract 48, add 18. So what the heck is that? Negative 48 plus 18 is negative 30. Negative 30 plus 12 is 18. And then so x is 18 over 66. But I believe we can divide 6 out on the bottom and get 11. And then 18 divided by 6 is 3. And so x is 3/11. Oh, and I think I forgot a negative sign up here. Yeah, negative 48 plus 30 is going to be negative 18. So this is negative. So the final answer is x equals negative 3/11. Now, does anyone see an easier way to do what I just did? Because multiplying by 36 kind of made the numbers bigger. It didn't necessarily make it too much harder, but I could have multiplied by a smaller number. Does anyone know what number I could have multiplied this by? Anyone want to take a stab? Well, what I did was I just multiplied all the denominators together. Really, the easiest way to do it is to multiply the least by the least common denominator. So the least common denominator here is, since 3 divides 6 evenly, and then 2 divides 6 evenly, I really only needed to multiply this equation by 6. So by doing that, a lot of these bigger numbers would be smaller as I solved it. But the foolproof way of doing this is just to multiply the denominators together, get your number, and then multiply that number by every expression in the equation, because you'll still get the same final answer. Okay? So again, the steps: eliminate the fractions, simplify the expressions, and then solve for the variable. Okay? All right, there's one more type of linear equation in this section, but it will it's a linear equation, but it could involve other variables that are just unknown at this point. So let's say you get something like this. Let me see what I'm looking at here. Let's say s equals, there's just lots of variables in this one, 2 times L times W plus 2 times L times H plus 2 times W times H. In Scranton, we say that's a H, right? What we're interested in solving for is, let's solve for H. Because solving equations like this is going to be important in the next section, which I'm actually going to be able to start today. Okay, so we're going to solve this for H. So it would just be like, we have to pretend that all the other variables are just numbers, all right? So that means any expression not involving H, we're going to put all on one side of the equation. So this S over here doesn't involve H, and then the 2LW doesn't involve H either. So I'm going to subtract that from both sides. So I get S minus 2LW equals 2LH plus 2WH. All right. Now that I have all the H's on one side, I want to factor these two expressions to isolate the H. So there's only one H in each, so I put the H in front of, so I'm basically finding the greatest common factor, but only with the H's. So that's an easy one. That's just the two H's, right? So then we're left with H times 2L plus 2W. And again, if you had to check that, just redistribute the H to see if you get the same thing. And then finally, since 2L plus 2W is just a number, to isolate H, I divide both sides by that expression. So I get my final expression is S minus 2LW all over 2L plus 2W. So that would be the final answer in terms of isolating that variable h. Okay. Now you're going to see more of this, so I'm only going to do this one example here. But that actually wraps up section 1.1. So are there any questions about anything I've done so far? If you want to put your hand up, or everything's good. I did see some thumbs up. I think they're just probably okay. No problem. All right, so just quickly review this section. Now, I mentioned to a couple people that once you get past the P sections, each section is sort of very specific on what you have to do. And now this one was really specific, right? All we did was, all right, we talked about the domain, right? So find the domain of equation. And I gave you the different types. You could either have ones that are all real numbers, ones with rational expressions where maybe one value doesn't satisfy the domain. We solved equations, and that process was the same from here in the notes all the way down to the bottom, right? And then we just had a few definitions about equations that are either inconsistent or identity. So there's really not much going on in this section, and a lot of it was probably a review. So here we go. The homework, and this is going to be on page 89. Okay, page 89 in the book. Very simple, 15 through 47. And then I'd also like you to do 55. Well, it's 14 through 47 odd. And then 55 and 57. All right, that's the homework. Now, it's a Thursday, I think, right? So you're going to put this homework in the Dropbox by next class. All right. Now this will be the first homework for exam 2. So if you hand this in and it's satisfactory, you'll get plus 2 points towards exam 2. All right. All right. Wonderful. Great. And again, these sections are a little smaller than some of these other ones that we've been dealing with. So that's section 1.1. So, we're just going to move right along here. And I'll write in section 1.2. Okay. Section 1.2 is applications of linear equations. And I'm going to tell you right now, you're not going to be happy what's in this section. Sorry, just to burst your bubble on this one. But here you go. So this entire section is devoted to word problems. All right, so you probably all just cringed, right, when hearing word problems. In math class, word problems are always the worst things, right? They're always terrible. Can I get a thumbs up from people who think word problems are terrible? Just want to see if you're all still listening to me. Anyone? No one thinks word problems are terrible? No thumbs up? There we go. All right, thanks, Robert. I appreciate that. Okay, Brendan. All right, great. All right, so I'm seeing some people. Yeah, you're clicking me. All right, you hate word problems. Got it. Oh, and I'm seeing some thumbs up from Terrence there. Excellent. Perfect. Okay, but I'm going to try to make this as easy as I can possibly make it. So what I'm going to do is I'm going to do some examples right at the end of the chapter, because in the actual examples in section 1.1 of the book, again, they're giving you examples, but each example is different, and then the word problems in the homework, which I won't give you any more homework from this section today, but the homework problems are different. So what I'm going to do is I'm going to solve word problems directly from the end of the section, and then when I do give you homework, it'll probably be on Tuesday, all you'll have to, I'm going to give you the homework types that are the same type that I'm going to do here in the notes. So it's not that you're going to have to worry too much about different problem types, because you can always reference these notes when you're doing the homework. Okay. Okay. With that being said, again, there's 1,000 things going on my computer. I need to, I already oh boy. I have little snapshots of the ones that I want to do at the end of the chapter in class. They're in my old math folders here. So section 1.2 probs. So I'm going to end up doing 7 examples, and then I think I give you 6 for homework. Okay? So here's the first one. I'm going to make this a little bigger. And I don't know, I guess this could be, applicable at some point in real life. Sorry it's sort of rotated like that, but what are you going to do? Okay, here we go. So it says, and essentially what we're going to end up doing is trying to write out a linear equation. So we have an air conditioning repair bill for $229.50. That seems like a lot for an air conditioning repair bill, but whatever. Showed a charge of $72 for parts, with the remainder of the charge for labor. All right? So they say, let X equal number of hours of labor it took to repair the air conditioner. And it says, write an algebraic expression for X for the labor charge per hour. All right. And this is from my book, so the answer is there. But I'm going to show you how you'd walk through a problem like this. First thing we want to do in word problems is label out some variables. Okay, so we know the total, and this also helps with partial credit if you suck at these problems. Okay, so we're going to have the total bill. Okay, we know what that is, so we'll use an equal sign. Is $229.50. All right. Now, what we want to do for this total bill, because we want to write an expression first. The total bill, let's call that T. All right, so lowercase t is going to represent the total bill in my linear equation. What's the next thing they give us? So they talk about parts, right? They say the parts cost, and we know what this is $72. All right, well, let's call that P. The parts cost is P. All right. Now, in terms of the rest, it says X is the number of hours. So they already give us that. So the number of hours of labor now we don't know what it is, so we'll just leave it as X. We don't have a number for that. And then they want write an algebraic expression for X into labor charge per hour. So we're going to say the labor charge per hour, right? So in real life, what this would be, and this is how they always get you. Well, I'll put this in parentheses or quotes. They get you, like when they're installing something on your car, and you look at the bill, and it's like the part costs $15, but your bill's $150. It's because they're getting you on the labor it took a mechanic to fix the thing. So labor charge per hour, that would look something like, it'd be like $50 per hour. Okay. And we have to make that variable up name. So let's call that L for labor charge. All right, so this is one thing you could do in any of these problems. It's just outline and then describe all the variables that are going to come up in this problem. Okay, so here's how it's going to work. We have to now make a linear equation using these 4 variables. All right, and they're just assuming you could read this question and understand how this is going to work, or how bills work. All right, so when you have a bill of sale, right, and again, I'm going to write this out just in case people don't know. Bill of sale, right? You have your individual line items, right? So you have line item 1 is so much, line item 2 is so much, and then you have a total on the bottom, right? So to get the total, you're basically adding these together. Right? So they're assuming you understand what a bill looks like. And I'm assuming you've all went to a restaurant and sort of seen that. So how do you make an equation out of this? Well, so we know the total. So I'm going to call this T, right? That's our variable. The total has to equal the sum of 2 things in this problem. It's the parts cost, which is P, plus the cost for the labor. All right. Now, how do we figure out the labor charge, right? We want to get this 50 here. So won't the labor charge just be X times L? Right? Because if X is the number of hours, and this is called unit analysis, right? So this would be hours times money per hour. That's what L is. The hours would cancel and you'd be left with money. Okay. So here's our linear equation. Once you get to this point, plug in all the numbers that you know. Some people have a different philosophy of, oh, why don't you solve for the variables first and then plug in the numbers. I'm a plug in the numbers guy first. I find that most students are also that way, so that's the way I like to do it. So I'm going to plug in the numbers I know. So I know the total is 229.50. The parts charged, P, is 72. And again, I don't know X or L. But they'd like an algebraic expression or a linear equation in terms of X for the labor charge L. So what we have to do here is solve this equation for L. So we're going to do 229.50, and I'm going to subtract 72 from the right side, equals X times L. And then I'm going to solve for L by dividing by X. So you get 229.50. I'm not sure why they don't actually do this subtraction, but there you go. And then divided by X. So you'll see that that's actually the answer in the problem, right? 229.50 minus 72 divided by X. All right? So that's our final answer, the algebraic expression for the labor charge per hour. All right? Again, word problems, they're kind of, okay, annoying, and sometimes it's hard to figure out what's going on. But again, the one you would be assigned for homework is going to be something very similar. But any questions on this number 12 at the end of the book for section 1.2? Okay. Seeing none, let's give another one a shot. Okay. The next one is going to be number 20. Okay, so I got to get out of here. Hopefully it opens up to the same. Oh, it did. That's magical. Okay. Actually, it's funny that I use that word magical. Anyone ever watched the series Sons of Anarchy? No? No one's seen this show before? John, no? These are no's? No shows? Really? Oh, well, then this is going to be... Oh, it doesn't even matter then. I don't know. There's a character. He's the sheriff, and he's kind of helping these outlaw biker guys. And he has to crash a car. And he always has funny lines, and he just goes, after he crashes the car, he goes, another magical day to be alive. And I think it's just one of the funniest lines that character has ever said. And if you think about it, I'm teaching a class in my office, talking to a tablet, and I don't know where everyone else is, but I don't know. I think this whole thing is just absolutely ridiculous. So again, another magical day to be alive. So here's the next question. This one, everyone's probably had a situation like this, right? So a pair of sneakers is on sale for $68. All right? If the original price was reduced by 15%, what was the original price of the sneakers? Okay. So let's write some things out here. Okay, sale price, $68. Let's call that S. All right, sale price, S. All right, was reduced by 15%. So this is the reduction. All right, 15%. We'll call that R. Now, when we're dealing with percentages and we want to see how that changes integer values, we're really going to use the decimal version of this. Kind of like when I was showing you how to calculate your current final average in the course. You know, anytime you have a percentage, you're going to use the decimal. So you're going to see we're going to use 0.15 here. So this is the reduction. And let's see, we are looking for the original price. We don't know what that is, but let's call it P. Okay, so somebody take a stab at it. Who's brave enough? Write this out. What would this look like? So we're trying to think about when you're in a store, right? And you see, let's say something's $100, right? Yeah, Kaylee, go for it.
Would you do 68 times 0.15?
So if we did 68,
that would be 15. Would you divide it actually?
Okay, so I think you're going to end up dividing, but it's not going to be by the 15. So let's just do a simple example. Say you bought your I don't know what stores you guys go to. I'm an old man, so I'm going to Kohl's, right? I gotta go pick up khakis or some stupid pair of clothing, right? So I got $100 pair of khakis, but they're gonna give me 15% off, right? So how do you figure what 15% is? Well, this one's easy, right? 15% of $100 is $15, right? So if I want to figure out the sale price, I do 100 minus 15 equals $85. So my sale price here is 85. Does that make sense to everyone? Like, that's how you would figure that out. Now, sometimes they don't give you an easy number like 100, but that's how you would figure out the sale price. So here's what it's going to look like. It's going to be original price P minus the reduction percentage times P equals the sale price. Does that equation make sense given my example down here, Kaylee, just because you still had your hand raised? Does that make sense?
Yes, that makes sense.
Yeah,
Thank
right?
you.
So sometimes when you're doing these word problems, and it's a real life situation, and they're all real life situations, the ones that I've picked. Just try to make an easy example out using the numbers, because then this right here probably definitely helped you realize that, oh, it's the original minus the reduction percentage times the original equals the sale price. Okay? All right, so now that we have that there, let's plug some numbers in. I'm going to get rid of this just so there's more room for the actual answer. Okay, so what do we know? We don't know P. We'll leave that there. But we know the reduction percentage. But again, we're going to put it in decimal. And then sale price was $68. All right, so we can actually do this subtraction on the left-hand side, right? Because there's really a 1 in front of this P. So 1 minus 0.15 is going to be 0.85 P is 60 equals 68. So the P, the original price, is 68 divided by 0.85. And when you do that, you're going to get $80. And I believe that's what the answer is there in the book. Okay. All right, any questions on that one? Okay. All right, just one last thing. I just want to make sure. Is Eamon here? No Eamon? How about Anthony Scarlata? Did he come in? Okay, great. Everyone else is here. All right, so that is going to wrap up what I do today. But before you all disappear on me, just a quick recap. So I finished section 1.1. The notes are up there. And then again, this video is going to be posted. So if you want to review anything from the video, please go ahead and do that. The homework from section 1.1 is going to be doing the Dropbox by the start of next class on Tuesday. And then I started a little bit of 1.2, but don't worry about doing any homework there because I'm still not done with doing those problems. Okay? So this is how it's going to be. We're before with section P, it took maybe one whole class or one class and even a little bit more to finish a section. Well, the sections in the rest of the book are actually a lot shorter, and they focus on smaller amounts of material, which I think actually makes it a little easier because there's less things to actually worry about. Like in section 1.2, you're only going to have to worry about these types of problems, and I think they're going to be pretty easy once I go through them all. Okay, so we might see a section and a half about every class. It really depends on the section. Okay, so that's it. I hope everyone has a good day. I hope our first virtual class was reasonable. If you feel like you want to be asking more questions, that's fine. You could certainly always interrupt me. I don't really care about that at all. I know some professors don't like to be interrupted, but like if you see me doing something and you're just like, what the heck is he doing? Just feel free to chime in and I'll try to explain it a different way. All right, everyone have a great day and I will see you on Tuesday. All right, have a good one.
Thank you.
Thank you,
See ya.
Professor. Have a good weekend.
You too. All right, see you.
Thank you.
You're welcome.
Okay.